So this is a pretty trivial example asking us to apply Ohm's law as well as the definition of conductance and power in a resistive circuit. As you can see from the schematic, we have an ideal current source with a rated terminal value of 4 milliamps. Since it's an ideal source, it will produce whatever necessary voltage across its terminals in order to provide a current of 4 milliamps, regardless of the resistance of the load. In this case, we have a relatively large load, 5 kiloohms. So the question is, how much voltage must the current source produce in order to drive that current through the resistance? That's the first thing that we want to determine. And that can be simply determined by Ohm's law. In order to find the voltage across that resistive component, we take the product of the current through it times its resistance. By definition, that's 4 milliamperes times the resistance value of 5 kiloohms. In terms of the coefficients, 4 times 5 is, of course, 20. And we're fortunate in that the prefix of milli and the prefix of killi, which have orders of magnitude of 10 to the negative third and 10 to the positive third, respectively, when multiplied together by the power rule, cancel, leaving us with no prefix and simply units of amps times ohms, which is a volt. 20 volts. For the second quantity, which we're asked to find, that is the conductance, measured in an SI unit of Siemens. By definition, it's simply the inverse of the resistance value of the component, which in this case is 5 kiloohms. So dealing with the coefficient, 1 divided by 5, same as 2/10 or 0.2. When we have a killi or 10 to the third in the denominator, that moves to the numerator as 10 to the negative third. 1 over ohms, by definition, has a unit of Siemens. Now, in this particular case, if we wish to place that quantity into engineering notation, I need to increase the coefficient 0.2 by 3 orders of magnitude, which would make it 200. If I increase the coefficient by 3 orders of magnitude, I need to reduce the exponent of 10 by 3. So that would be times 10 to the negative 6 Siemens, or simply 200 microsiemens. And finally, we're asked to calculate the power, and in fact we have 3 different ways which we could approach it now, but given that we know both the current and the voltage, we'll simply take the natural definition of I times V. That will be 4 milliamperes multiplied by the voltage found in part A of 20 volts. Of course, 4 times 20 would give us a value of 80. The prefix milli, no prefix here, carries through, simply milli. And an amp times a volt is a watt. That's a positive quantity, as we'd expect, and I should say by the passive sign convention, we didn't need to append a negative there, since the current falls down the potential gradient of the component, entering at the positive terminal. That positive value indicates that the passive component absorbs power, as we'd expect by definition of a resistor.